Hello guys, in this video I'm going to talk about SymPy. SymPy is a Python package that can deal with symbolic arithmetic, symbolic math. I've already done two other videos about SymPy. In this video I'm going to show you how SymPy deals with rational numbers, rational expressions, logarithms, and exponentials. And I will leave the link in the description below for the other videos I've done before, and also to a playlist with all these videos about SymPy. So the first thing that I need to do is to actually run this cell to define some symbols. So I'm going to define x, y, a, b, c, d, and n. And these are the symbols that I'm going to use throughout this video. So let's run this cell, and we have here our symbols defined. So first, let's talk about rational expressions. Any function that can be expressed as a ratio or a quotient of polynomials is called a rational function. Okay, we're not going to define functions in this video, so we are going to talk about rational expressions, okay, without the equality. So SymPy does not combine or divide rational expressions by default. So here we have this expression a over b plus c over d, and if we run this cell, the output, the result, is actually a over b plus c over d. Okay, but we know from math that we can join these fractions doing the LCM, the least common multiple procedure. So if you want that, you can use this together function of SymPy. So here we have SymPy.together and a over b plus c over d. If we run the cell, we have here the result of the LCM procedure. We have here a times d plus b times c over b times d. Okay, so SymPy does not combine rational expressions by default, but you can ask for this combination using this together function. What about the opposite? So here we have a rational expression, and I want to write this expression in the form of simpler fractions, okay? What we used to call partial fractions. And this is something that we use a lot when you are doing integration of rational functions, okay? So let's run this cell. And as you can see, SymPy only represents the expression that you passed in the cell. But you can ask SymPy to take apart this fraction, to represent this fraction in simpler fractions, okay? And we can use this apart function for this. So let's run this cell, and now you can see that this expression is now represented as simpler fractions. You can do the math and see that this form here is equivalent to this one. It's just written in a different form. Now let's talk about exponential and logarithmic expressions. The first thing that I want to talk about is notation. Most programming languages and libraries, they represent natural logarithm with log. But we know that usually we use ln when we are writing and making hand calculations. SymPy recognizes both notations. You can use ln like this, or you can use log like this, okay? It's the same. You can see that the output is the same. Even though you can write as ln, the output will be log, but many people will consider that this is a more friendly representation because we usually write ln when we are doing hand calculations, and most calculators use ln for natural logarithm. Most people will probably think of this log function as the logarithm of x to base 10, but it's not. It's the natural logarithm of x. Now let's take a look in these equations. Okay, we have here two equations, actually two identities that we usually see when we are studying logarithms. Okay, such identities are not valid if x and y are complex. They are valid only when x and y are positive real numbers and only when n is a real number. And let's see what SymPy does with these logarithms. Okay, so here we have the log of x times y. And if we run this cell, we see that SymPy represents as the log of x times y. SymPy didn't expand it to the sum of log of x plus log of y. Okay? The same thing happens in this second log. We can see that if we run this cell, we have log of x to the power of n. We didn't see the expansion n times log of x. But what if we want the expanded versions? What if we want this log to be represented as the sum of two logs? And what if we want this log to be represented as this multiplication? Well, SymPy has a function called expand log. So let's see what happens passing this expression to this function. So we can see here that apparently it didn't work, and let's do the same with this expression, and again apparently it didn't work. But I want to tell you that it did work. This is the expected behavior because when we defined these symbols, we didn't put any constraints. These symbols can represent anything, even complex numbers, and these identities are not valid for complex numbers. Okay? But let's say that you really want that SymPy will make the expansion for these expressions, so you can force the expansion using this force parameter in the expand log function. So now you have the sum for the first expression and the multiplication for the second one. But please avoid the use of force. It's not good to force things, you know? And I really like the Zen of Python. You can see the Zen of Python importing this, okay? So this is the Zen of Python by Tim Peters. And for those of you that never heard about the Zen of Python, the Zen of Python is the guiding principles that had some kind of influence in the design of Python programming language. And it's a really interesting list of principles, and I really like this second one. Explicit is better than implicit. I don't think that's a good thing to force behaviors. I think that a behavior should be natural. Okay? And how you can make things natural? You can define the symbols with some constraints. If these behaviors are really important, they should be made explicit in the definition of the symbols. So let's redefine x, y, and n. But now I'm defining x and y as positive numbers with this positive parameter, and I'm defining n as a real number with this real parameter. Okay, so let's run this cell, and now let's try again to expand the logarithm of x times y. And be aware that there is no force parameter here. Okay, I'm just passing the expression. And now you can see that the result is the log of x plus log of y. The result is the right-hand side of the first identity. And we can see the same behavior in the second expression. Now, if we expand this expression, we see that we have n times log of x. And this is the expected behavior. And now the expansion worked because we made the definitions with the right constraints. So to make it clear, if you know the conditions of each symbol, the constraints of each symbol, please make it explicit when you are defining the symbols. Make them explicit when creating the symbols. Okay? Now let's do the opposite operation. Let's do the combination. So now I'm passing the sum of log of x plus log of y, and I will use this function log combine to have log of x times y. And you can do the same thing for the other expression, and we will have the log of x to the power of n. Okay? So you can expand logarithm expressions and you can combine logarithm expressions. And finally, let's talk about the Euler number, the base, and the natural logarithm. It has several definitions, as you can see here, and SymPy has this representation e. Okay, so you can use SymPy.e with a capital letter to see the Euler number, and you can write the exponential of x with both e to the power of x or exponential of x with the x function, and we have the same result. If you want approximation, a numerical approximation for e, you can use the AND method. I've already talked about the AND method in other videos. Now running this cell, you can see here a numerical approximation for the Euler's number. And we can see, we can check that log really represents the natural logarithm passing e to the power of 2 to the log function, and we see that the result is 2. Okay, and if you want the logarithm in other base, you can pass the base as the second parameter. So in this case, we'll have the same result too, but note that I'm passing 10 to the power of 2 or 100, and I'm passing here that this logarithm is base 10. So you have the result 2 because this is the logarithm of 100 to the base 10. Okay, that's why you have here the number 2 as the result. So this is it for this video. I hope you enjoy it. If you did, please give it a thumbs up, and I will leave in the description below a link for the playlist of videos about SymPy, and also I will leave in the description below the link for my website, chemistryprogramming.xyz. I have a lot of articles there about many things concerning chemistry and mostly Python. And also you'll find an article there with all these examples and some more examples. Okay, so please visit the website. I know that you will like it. Okay, so that's it for this video. I see you in the next video.